Hey everybody, what's going on? It's me, your friendly neighborhood chemistry teacher. I'm here today to show you a lab that you're going to do where you're going to be determining how much salt is in two different samples of salt water, the concentration of them, sample A and sample B. So you're going to be figuring out their concentration of salt water based on their density. What you're first going to have to do though is you're going to have to investigate what relationship exists between concentration of salt water in a sample and its density. You're going to do that by testing a few different samples, one that is 0% salt, one that is 3, one that is 5, one that is 8, and one that is 10. For each of those samples, you're going to be measuring a mass for a certain volume, which will allow you to calculate its density. And you're going to create a graph, or what is called a standardization curve. That curve, or that graph, will show you the relationship between a sample's density and its concentration of salt in the salt water. Now that only works if sodium chloride is the only thing dissolved in the water. We could have tried to use conductivity, or how well the salt water conducts electricity, because that also increases with concentration of salt, but not in a linear way, the way that the density does. This will work pretty well. The relationship is going to be a direct linear relationship with a slope that you're going to figure out. And it works pretty well up to a concentration of around 25 to 30%. 30% is when the salt water is saturated, meaning no more salt can dissolve. And so it stops being linear as you approach 30%. But it works pretty well for other percents. Let's get to it. The procedure at each station is going to be the same. At each station, you're going to need to write down the percent concentration of the solution that you are testing. You will write down the mass of an empty beaker that you're using. You'll then look at where the water level is starting in the burette. You'll let out some volume of water into the beaker. Between 10 and 20 milliliters would be good, at least 10, because that way you get an extra significant figure. You'll take the mass of the beaker with the water, and then you'll note the final volume on the burette. It says to take the beaker mass for each trial. However, if you are going to bring your balance with you and use the same beaker each time, then that's going to be the same so long as you make sure to dry it out each time. If you need to stop and use a different beaker because it's on different days or different times, or if you're using a different balance for each station, you'll want to get the beaker mass. Once you've gotten those things, you'll pour out your sample and dry it and move to the next station. I'm going to show you how to analyze them on LagerProbe. First, you're only given 2 columns, though you collected 5 columns when you went around to each station. And so we're going to put in 3 more manual columns and format these. Now I'm going to enter my data. I'm going to rename the dataset as just data. I'm going to create a new dataset that will be the calculations to keep them separate. Now, in calculations, these will be calculated columns, not manual columns, and so I'm going to have to not just rename these, but delete them, because they will be a vastly different format. So for the calculations, you need to get the mass of the sample, you need to get the volume of the sample, and then the density of that sample. This first one, mass of sample, is the difference between the beaker with water and just the empty, dry beaker itself. The volume of the sample is the difference between the final and initial volumes. The density is going to be the ratio of the mass to the volume for that sample. Now we're going to change our graph so that it graphs the percent from the data and the density from the calculations. I'm going to perform a linear fit to get the line of best fit on here, as well as to get the equation for it. And what this tells us is that the density equals this slope times whatever the percent concentration is, plus this y-intercept, 0.9976. The y-intercept in this case also represents the density of a pure water sample, since the percent is 0 and the density is here. So it's telling us that a sample with 0% salt should have this density. This slope means that as the percent increases by 1 in terms of concentration, that the density goes up by this amount, 0.007126 grams per milliliter, for every percent that you increase the salt concentration. You'll use the equation for this line to use these two densities for the two unknowns and figure out what percent concentration they are. If graphical analysis is the program you have, you're going to need some functions that require the full version, and so if you have yet to get the unlock code from your instructor and unlocked the full version, you'll want to get that and enter it in the bottom here, and then go to manual entry. If you don't get a table to start off, make sure that you select one. And we have only 2 columns, but we had 5 columns of data. So we're first going to rename these and then add in 3 more. And now I'm going to be putting in my values. Next, you're going to add calculated columns, and what you're going to need to calculate will be mass, volume, and density for each of these. And the mass of the sample is going to be the difference between the beaker with the sample and just the beaker mass. The volume will be calculated as the difference between the final and initial volumes. And the density will be the ratio of the mass to the volume for each sample. Now we'll change our graph formatting. Here we get our linear fit with this equation that y equals mx plus b. Y, remember, is the density, so the density equals m, this slope, times x, which on the x-axis was percent concentration, plus the y-intercept, which is 0.9976. Now, what this y-intercept represents is the density of water that has 0% salt in it. What the slope represents is that by every 1% concentration of salt in the salt water, that the density increases by this amount. I'm going to create a new data set that will have the unknowns. It's going to format everything the same way, and so the percent concentrations are not known, but the unknowns are A and B. All I have to do is put in my data and it will give me the densities. All right, so now I've got densities of unknown solutions. So I had to reformat those from this to make sure that it was going to select the values from this unknown data set rather than selecting values from the previous data set. Though now I get some densities that make sense for these. I'm going to use this equation now, plugging in this density for y, using the m and the b to solve for x, the percent concentration. And I'll do the same for b. All right, so now that I've collected all the data, I forgot to show you how all those things were created so that you understand the amount of precision. So that's what I'll do now. But to do that, I've got to turn back time to get there. So I'm going to take my clock, I'm going to modify it. And we're going to go back. All right, so now that we've turned things back to 1:37 in the afternoon, I can show you how these were created. First, I needed to calculate how much salt would go into each solution. I made up 2,000 milliliters or 2 liters of each solution. These are percent solutions, and so that means that if, for instance, something is 3%, it means that in every 100 milliliters of solution that there were 3 grams of salt. Scaling that up means that the 3 there is 20 times as much as the 100 milliliters in this container, this volumetric flask. And so I needed to multiply the 3 grams in 100 milliliters by 20 and get that there should be 60 grams in 2 liters or 2,000 milliliters of total solution for the 3% solution that was created. Now I'm using a volumetric flask because the volumetric flask will give me great accuracy and precision using the same flask to create each solution. The volumetric flask is accurate to 1 milliliter. And so when you're doing your calculations to figure out what percentages each solution was, even though one says 3%, it's actually much more precise because the balance will give 3 decimal places, and so the 60.000 grams would be 5 significant figures. And the 2,000 milliliters, because it is to the nearest milliliter, because of the accuracy on this, would give you 4 significant figures. And so though the bottle says 3% salt water, you really can consider that to be as precise as saying 3.000% salt water. So I'm going to show you how the solutions A and B were made. I'm going to be measuring out the amount of salt now for solution A, unknown solution A. Now for solution A, it's going to be 140 grams of salt in 2 liters of water. So I'm going to zero out a beaker. I'm using canning and pickling salt because it does not have the iodine as iodized salt does. And there we go. Next, all of the salt is going to go into the flask using the funnel. To ensure that every grain of salt that I measured out is going to get into the flask, I'm going to first start pouring water into the flask from this beaker to rinse out any grains of salt. I'm now going to fill this the remainder of the way, mostly using the sink until I get to about here, and then I'm going to use the beaker just to get to the exact mark. Next is going to be to bring this over to a stir plate and mix it up. Next is to make sure all of the salt is dissolved. I'm going to use a stirring plate with a magnetic stir bar. This stirring hot plate has controls for heat and for stirring using the magnet. Now, through that process, the volume went down as the water and the salt mixed. Some trapped pockets of air were escaping, and the overall mixture, once things are thoroughly mixed, actually takes up less space. So I'm going to top this off again with water. Now it's time to split this up into bottles. Now they all get cleaned up and get labels. And there you have it, solution A complete. Solution B is going to be made the same way, with the amount of NaCl being the only difference. Those will be having 240 grams of salt per 2 liters of water. Well, thanks for watching. I hope this sets you up to do well for your first full lab write-up. So work through it, work at your own pace, take your data carefully, and I'll see you in the lab. Toodles.